Hello everyone, welcome back to the channel. So today we are going to solve this question called Xorificator 3000 from the recent Division 3 contest from Codeforces. So question goes like, Alice has been giving gifts to Bob for many years and she knows that what he enjoys the most is performing bitwise XOR of interesting integers. So interesting integer is an integer such that when we take the remainder of that integer when divided by 2 to the power of I, that should not be equal to k. So such integers are called interesting integers. So therefore, this year for his birthday, she gifted him a super powerful Xorificator 3000, the latest model. So Bob was very pleased with the gift as it allowed him to instant compute the XOR for all interesting integers in any range from L to R. Okay, so any range from L to R. So for some reason that xorificator got lost or something happened to it, so we are given a task to implement the same xorificator. So input will be given like L, R, I and K, where L is the left limit of the range, R is the right limit of the range, I is power to be raised of 2 and to be taken mod with something integer x, and k is this remainder that should not occur to uh, for an integer to become interesting. So yes, this is basically the question. So when we look at the constraint, we okay, let's take a look at uh, possible solution. So we know that as given in question as well, it is a hint that unfortunately the device was so powerful that at one point it performed XOR with itself and disappeared. So basically it is saying that as we all know, suppose 10 XOR 10 will always be 0, or you can say x XOR x will always be 0 because XOR is self inverse operation, right? So if we do x XOR y XOR y XOR you can say z, then this should give you x XOR z. So this XOR y and this XOR y gets cancelled because it is self inverse operation, that's why. So this is basically one of the hints from the question, you can say. And suppose what I can do is that I can calculate the XOR of all the elements, suppose from L to R minus L plus 1 elements will be available. So I will calculate XOR of all the elements. Suppose you can say XOR of all elements from L to R is suppose XOR 1. Okay, the result is XOR 1, and just we have to take the XOR of the elements which were not interesting, means they though them what you can say, they were uninteresting. So if we take the XOR of all uninteresting, or you can say not interesting numbers. Okay, so this is XOR of all the numbers possible from L to R, and this is if we take XOR with all the uninteresting numbers from L to R, we should get our answer to be outputted, right? So this is one observation that we can make. And one more thing, I don't know how to calculate the, okay, first of all, let's take a look that how can we calculate the XOR of all the elements from L to R. What I can do is that I will calculate XOR of all the elements from 0 to R, okay, and I will calculate XOR of all the elements from 0 to L minus 1. So suppose this is result 1 and this is result 2, and if I do result 1 XOR result 2, then this should give me this XOR 1, right? So because XOR is a self inverse operation, we have just seen that. And yes, so what can I do to calculate XOR of all the elements from 0 to R in a quick manner? Okay, so there must exist some formula or some efficient method because our constraints are too large, right? 10 to the power of 18. So that's why. So one more interesting property about mod is that, suppose mod or XOR, XOR from 0 to 1 is, you can say, 1, right? Because 0 XOR anything is just that number x, and XOR from 0 to 2 is 3, XOR from 0 to 3 is, you can say, this is 1, this is 2, and this is 3. So it is going to be 0. Okay. Yes, it is pretty obvious because why obvious that from 0 to 2 the mod is 3, and when we mod the 3 in this result, so 3 XOR 3 should be 0, right? So that's why it is 0. And for 0 to 4 it should be 4 because 0 XOR 4 will be 4. And for 5, from 0 to 5, you can notice that it is 1. Okay, so when you go along calculating XORs in this way, 0 to 6, you can say 0 to 7, 0 to 8, you will notice a certain pattern. Okay, so what this pattern is, that if percentage 4 means modulo 4, if it is equal to 0, then answer will be, suppose you can say r percentage 4 is 0, then answer will be r, means XOR of all the values from 0 to r will be r. If r percentage 4 is 1, then answer is, means the XOR of all the elements from 0 to r is 1. And if modulo is 2, then XOR of all the elements from 0 to r is r plus 1, I think. And if r percentage 4 is 3, then XOR of all the elements from 0 to r is just 0. Okay, so this is the very fast way to calculate. So this is by observation, or you can deduct it by some mathematical reasoning as well, like we did before for the case of, you can say, 3 and 4 and 5. So this is important result. So we can get this thing, r1 efficiently, r2 efficiently in o of 1 time. We can calculate these both in o of 1 time. Okay, so what I need now is that XOR of this all the uninteresting numbers. Okay, so another way I can model this question is that, you can say, suppose I will define my function, you can say f of r. Okay, f of r is the answer when left limit is 0. Okay, is the answer when left limit is 0. So it is basically the answer when left is equal to 0 and right is equal to r. Okay, so can I say my final answer will be f of r did XOR operation with f of l minus 1? Do you agree, folks? Do you agree? See, why? Because suppose some numbers will be there, 0, 1. Okay, wait, let me do it with black ink. 0, 1, 2, 3, so on up to, suppose, l minus 1, l plus 1, l plus 2, and so on up to r minus 1, and you can say r. So what my answer basically is, what my answer is basically that you do XOR of all these elements and do XOR one more times with all the numbers which are uninteresting, right? So what I can do is that uh, wait so I will find all I will try to find all the uninteresting numbers from 0 to r. Okay, so some numbers, let's say 2, suppose some numbers are there which are uninteresting, and uh, basically these are some numbers which are uninteresting. And for answer I can say that f of r is defined as, see, f of r is the answer when my left limit is 0 and right limit is r. Okay, so basically if I do f of r or f of l minus 1, it should give me my desired answer. Why you can argue that f of r is taking the XOR of these uninteresting numbers as well. Okay, uh, these uninteresting numbers as well, but this f of l minus 1 is nullifying that effect, right? When we do XOR with f of l minus 1, it is nullifying the effect of, wait the effect of uninteresting numbers from which are less than l, right? So this should suffice, right? Okay, so this is the definition of our f of r. So now you know that you can calculate XOR of all elements from 0 to r, right? We can do that in O of one time, you can say. We can do that in O of one time. So how to find the XOR of all uninteresting numbers, and then finally XOR it with our this result, right? This result to calculate f of r. So what I can notice is that uh, suppose 2 to the power of I is the number, right? So the first in uninteresting number will be k, right? Assuming that k is less than 2 to the power of, right, I, right? So first uninteresting number will be k. Second uninteresting number will be k plus 2 to the power of I, right? The third uninteresting number will be k plus 2 to the power of I plus 1, you can say. The fourth uninteresting number will be k plus 2 to the power of I plus 2. Now how can I represent these? So take a closer look. So suppose k's binary representation is something like, suppose it has some n number of bits. So b n minus 1, b n minus, oh, b n minus 2, b n minus 3, so on up to b2, b1 and b0. So suppose this is the binary representation of k. This is the string consisting of only zeros and 1. So what about binary representation of k plus 2 to the power of I? What will be it? So you can say, let us give this name a string, let us give this string a name, binary of k. Okay, so binary of k plus 2 to the power of I will be some, here it will be 1, then some bunch of zeros, and then here binary of k, right? We don't know how many numbers of zeros of course it can be calculated, but some number of zeros will be there, maybe 0 or some greater than 0 number. But basically k plus 2 to the power of I will look something like this. Okay, so uh, and what about binary of k plus 2 to the power of I plus 1? How will it look like? So basically it will look something like 1 0 the same number of zeros, this segment, and then binary representation of k. Do you agree? Yes, it is like that. You can take some examples and verify as well. So otherwise, you just add 2 to the power of I in this binary form, and then you'll get this string, right? So you can add, 2 to the power of I to get this result. Okay, so yeah, then binary of k plus 2 to the power of I plus 2 will be 1. It will be 1 1, same number of zeros in this segment, and then binary representation of k, you can say, right? So this is how it's working. So to calculate the XOR of all of these numbers, you can say that, suppose uh, this segment, okay, this segment of zeros will not contribute any bit in the, you can say, any set bit in the our result. So if the number of these uninteresting numbers is even, suppose it is 2, then the last n bits, because the size of k in binary is n, so built-in pop count, you can say, or you can calculate by that, and it will be n zeros, okay? Or otherwise, if it is odd, you can say it will be binary of k, right? Because binary of k done XOR with binary of k will just be 0, right? And if you do binary of k again, XOR it again, it will simply be binary of k. So last n bits just depend on what is the number of uninteresting numbers from whatever range you are calculating. This won't contribute any set bit to our final answer. And what about these? What about these? So see carefully, these bits. Isn't it like bits from, isn't it like XOR from some 0 to some number num? Right, because it is 1, it is 2, it is 3. Just see these two bits, right? So the next number will be 100, right? So it is 4. So it is basically the XOR of all the numbers from 0 to num, where num is these numbers, right? So that is the key observation, right? So this you can also calculate in O of 1 time, right? Can you? Yes, we can. So this is basically the thing, and when we calculate this thing, we have to shift it by I, right? Shift it by power, because we have to account for these positions as well, right? So that is basically the solution. So we will do this for f of r, right? And we will do this for f of l minus 1, and finally take the XOR of both, and then this will be our answer. So yes, let us take a look at the code. So LR and PK, P is basically the I, it because uh, we need I for, you can say, it, you can take I as well, but I is like iterator, like, right? You use it in for loop, so I thought P is more convenient for me, so I named it as P. I am keeping those as global variables, so need not to pass them into the function. So I'm taking the input, and then f of r is just f. I'm giving the name of function as only f, and then f of l minus 1, and then finally outputting this thing, the XOR of the two, f of r and f of l minus 1. So let us take a look what is our f doing. So fairly simple code. It is much higher rated problem. I can say it was 1900, but yeah, fairly simple code. This is the function which gives the XOR, like we discussed here. So this is important thing. You cannot what you can say, cannot forget this, so try keeping it in your mind. And what is our function doing? So basically it is initializing answer. The answer is the thing which I am returning finally in the function. So function returns long. Answer is give XOR of r, means the XOR of the elements from range 0 to r. And if k is greater than r, what you can see here is that if k is greater than r, so there is no need to do this thing, right? If k is greater than r, there is no need to do this thing, right? Because we are, means all these elements are the uninteresting numbers from 0 to r, right? So if our first uninteresting number is k, but if k is greater than r, then this whole thing doesn't make any sense, right? So that is why, so just returning the answer. And if k is less than or equal to r, what this t1 is doing is that, so let me show you. This is also important in math related problems. So how can I know that till where to go, right? So this last uninteresting number should be less than or equal to r, right? So the last uninteresting number should be less than or equal to r, right? So to ensure this, our uninteresting numbers are in the form of k plus some multiple uh, beta. What is beta doing here? Nothing. Multiple into 2 to the power of I, right? So this is the thing. uh, Wait, is this multiple? Yes, this is multiple, right? So here it should not be I plus 2, sorry. So here 2 to the power of I plus 1, here it should not be 2 to the power of I plus 1 into uh, 2, not 2 exactly. So wait, so they are just basically the representation of k comma k plus 2 to the power of I, k plus 2 into 2 to the power of I, k plus 3 into 2 to the power of I. So here it should be 2 to the power of I into 3. Okay, so that is the thing. So that's why k plus multiple into 2 to the power of I should be less than or equal to r, right? So we want to find this multiple to get the number of uninteresting numbers that are in between range 0 to r. So this multiple is less than or equal to r minus k by 2 to the power of I. Okay, so this less than or equal to can be just replaced by equal to because of integer division that our C++ performs. So multiple will be r minus k to the power k by 2 to the power of I, right? So in pure mathematics you can say this, right? So yes, mm, this is our multiple. And how many numbers will be there? So k plus k comma k plus 2 to the power of I, k plus 2 into 2 to the power of I, k plus 3 into 2 to the power of I. So if the multiple is 3, then our numbers, means number of uninteresting numbers, will be 4, right? So these are 4 numbers, so it will be mul plus 1, right? So this is needed because we need to know how many times this number is occurring, right? Because the final we have to consider to take binary of k or not. And also the number is needed for calculating this XOR, right? This XOR. Yes, it has become a bit messy, but okay. I hope you understood the solution. So let us take a look again at the code. So basically temp is give XOR of t1. So basically t1 is this thing. And why give XOR of that multiple only? Because multiple uh, multiple is the representation of these last bits, right? It is the representation of that. So that's why gives her of t1. Then left shifting it by p, because we have to uh, counter or take into account this size, right? Some zeros and some binary of k, length of binary of k. So that's why. And what next? If t1 plus 1 percentage 2 is 1, then temp plus is equal to k. This is the thing that I mentioned. If there are even numbers, then you will take that. No, you won't take that binary of k. And if there are odd numbers, you will. So that is basically the thing. And finally you will XOR the temp with the answer and return the answer, basically. And finally you will output f of r XOR f of l minus 1. And yes, I hope you enjoyed solving this question and listening to the solution as well. So, for amazing mathematical ideas, or you can say competitive programming ideas, stay tuned to the channel. Consider liking the video and subscribing to the channel. Thank you for watching. Uh, I hope you uh, watch many of my videos, and yes, see you again.